Urgent, analytical tone. Modern applications face a strict physical limit. When millions of users interact with a system simultaneously, they generate massive, unpredictable spikes of data. If your architecture is forced to capture every single one of those simultaneous events in real time, the infrastructure will shatter. Traditional monolithic architectures handle incoming data synchronously. When an application generates a user event, it routes that specific record directly into a central database, holding the transaction open until the disk write is complete. This creates an immediate mathematical problem. If your application generates 20,000 events per second, but your database can only physically write 10,000 records per second, you hit a throughput bottleneck. The database locks up trying to process the overflow. The failure cascades. Because the database is locked, the upstream application hangs waiting for confirmation. User requests timeout. The server runs out of memory, and critical event data is permanently dropped before it can ever be recorded. To engineer a system capable of massive scale, you cannot simply build a faster database. You must separate the act of creating data from the act of processing it. This animated diagram illustrates Apache Kafka, the industry standard for decoupling real-time, event-driven architectures. Kafka eliminates the database bottleneck by acting as an intermediate, highly durable storage buffer. Applications push data into Kafka at maximum speed. Kafka stores that data in parallel, isolated tracks. Then, downstream systems pull that data at whatever steady rate they can safely handle. Here at Royal Research, we approach Kafka by moving past the basic concept of data transmission. To truly master this platform, engineers must understand the specific mechanics of workload partitioning, state management, and strict delivery guarantees. We will construct a robust Kafka pipeline from the ground up. We'll start with the generation of a single data point and scale up to a fully distributed, fault-tolerant cluster. By isolating these specific mechanical levers, you will see exactly how Kafka operates as a highly tunable distributed log rather than a mysterious black box. Data enters the Kafka ecosystem through the Producer API. This diagram shows a producer node capturing raw events, like a user clicking a button or a sensor reading a temperature, and pushing those records to a designated topic inside the Kafka cluster. Sending records across a network one by one introduces massive latency overhead. To optimize throughput, the Producer API utilizes batching. It holds individual data blocks in memory for a fraction of a second, groups them together, and transmits the entire batch in a single request. Developers can further configure the producer to compress these batches using algorithms like GSEP or Snappy before transmission, reducing the required network bandwidth. Once the batch reaches the cluster, it lands in a topic. A topic is a category name for a feed of records. Internally, Kafka divides every topic into horizontal parallel rows called partitions to allow for simultaneous writes. The producer decides which partition receives a specific record by assigning it a partitioning key. If a record has a key, say a specific user ID, Kafka hashes that key and forces every subsequent record with that exact same key into the exact same partition. This strict key-to-partition mapping is the mechanism by which Kafka guarantees the chronological order of related events. Because all actions from a single user go to a single partition, they are written in the exact sequence they occurred. Without partitioning keys, Kafka distributes incoming data randomly across all available partitions. While random distribution maximizes write speed, it makes the ordered processing of sequential events, like calculating a running bank balance, impossible. On the opposite end of the architecture, we have Kafka Consumers. Looking at our diagram, this consumer node is the downstream application responsible for retrieving and processing the stored records from the cluster. Kafka brokers do not push data to the downstream applications. Instead, the consumer actively polls the cluster at configurable intervals, asking for new records. To track what has been read, Kafka uses offsets. An offset is a sequential, immutable ID number assigned to every individual record the moment it arrives in a partition. The consumer uses these offsets as a strict bookmarking system. It tracks exactly which records it has successfully processed. When the consumer reads and processes a record, it commits the new offset back to the cluster, advancing the bookmark. Kafka can handle these commits automatically in the background on a timer. However, automatic commits risk advancing the bookmark before the downstream application has finished saving the data. To prevent this, developers implement manual offset management. The application tells Kafka to move the bookmark only after a complex database transaction is completely finalized. Mastering offset commits provides the primary defense against data corruption. It ensures that if the consumer server crashes, it knows exactly where to resume without skipping data or processing the same event twice. A single consumer node polling a topic works for low traffic, but as the producer pushes hundreds of thousands of messages across multiple partitions, that single downstream node will eventually reach maximum CPU capacity. To achieve horizontal scale, Kafka uses consumer groups. By adding more nodes and defining them as a single group, Kafka distributes the processing workload across multiple machines. The architecture relies on a fundamental rule. A single partition can only be consumed by exactly one consumer within the same group. This strict one-to-one mapping ensures sequential data inside partition 1 is read in order by server A, while partition 2 is handled by server B. You achieve parallel processing across the group without destroying the chronological order of the individual partitions. Because of the one-to-one rule, if you add a fourth consumer to a topic that only has 3 partitions, that fourth server will sit idle. There are no available partitions left to assign to it. Therefore, an application's maximum parallel throughput is hard-capped by the initial configuration of the topic. If you need 10 servers processing data simultaneously, you must create the topic with at least 10 partitions. Distributed systems guarantee that hardware will eventually fail. When an active server loses power, the pipeline must adapt immediately to prevent a data bottleneck. Kafka brokers monitor the health of the entire consumer group by requiring a continuous heartbeat signal from every active node. If a server crashes and misses its heartbeat interval, the Kafka cluster flags that node as dead. The partition assigned to that dead server is now orphaned. Kafka immediately initiates a protocol called rebalancing. It detects the active survivors in the group and automatically redraws the internal mapping to redistribute the orphaned partition to a healthy server. The newly assigned healthy server queries the cluster for the last committed offset of that specific partition. It uses that bookmark to resume processing exactly where the dead server left off. While this guarantees high availability, the rebalancing process triggers a temporary stop-the-world event. All message consumption for the entire group pauses for a few milliseconds while the new assignments are calculated. This self-healing mechanism allows an event-driven pipeline to survive localized hardware failures and maintain 24/7 uptime without requiring manual human intervention. Kafka's default settings prioritize speed. Out of the box, it does not guarantee perfect data delivery. Perfect reliability requires explicit configuration. This split-screen comparison shows producer acknowledgments, or ACKs. This setting dictates how many broker nodes must confirm they saved a message before the producer is allowed to send the next one. On the left, we have ACKs equals 0. The producer fires the message and does not wait for any confirmation. This provides the absolute maximum throughput, but if the receiving broker fails before writing the data to disk, the record is lost and the producer will never know. A middle ground is ACKs equals 1. The producer waits for a pingback from just the leader node. It's safer, but if that leader dies before copying the data to its backup replicas, the data is still lost. On the right is ACKs equals all. The producer must wait for confirmation from the leader and all synchronized replicas. You trade network latency for absolute data durability. The system must physically wait for the data to be duplicated across multiple servers. You cannot have the fastest speed and highest reliability simultaneously. The architecture requires you to choose. By combining specific producer acknowledgment settings with strict consumer offset strategies, engineers create 3 distinct delivery semantics for their applications. The first is at most once delivery. The system is fast but lossy. If a network error occurs, the message is dropped. You use this for high-volume, low-stakes data, like tracking application logs, where missing a few rows has no impact on business logic. Next is at least once delivery. The system guarantees no data is lost, but if a network timeout occurs, the producer might retry sending a message that was actually successful, resulting in duplicates. This is used when data integrity matters, and the application can filter out duplicate records. Finally, exactly once delivery. This utilizes Kafka's advanced transactional API to guarantee a message is processed precisely one time, with zero data loss and zero duplication. It is reserved for critical systems, like financial ledgers and payment processing. The Royal Research Framework demonstrates that by tuning partitioning keys, consumer groups, and delivery semantics, you dictate exactly how your distributed log behaves under pressure. Mastering these first principles is the exact difference between deploying a fragile data pipeline and building a truly scalable, reliable, event-driven architecture.